What I wanted to talk about today is something that's almost by popular demand. Because many times we've been asked, can you help us out with the sort of issues we're looking at today? And it's a very difficult thing to do. It's the idea of how do you stress test your environment? How do you know that your database and its hardware can really perform as you need it to perform? Perhaps under increased load, and what's going to happen when you have twice as much activity as you do now? How should you size your hardware for a particular workload? It's really, really difficult to do this sort of thing. And what many DBAs end up doing is trying to write workload simulators. I've tried to do it a fair few times. It isn't easy. I don't think it's easy at all. I'm sure some of you have had a go. And if any of you have successfully written workload simulators that work for your environment, do please put in a comment. We'd be interested to hear about it, and perhaps other people should be as well. My own experience is that it's difficult, very difficult, to simulate with any degree of accuracy a realistic workload, particularly when you want to scale things up. So what will happen when the system gets so much more busy than it is now? It's also to do with sizing your environments. How many cores do you need? How much RAM do you need? And all that sort of thing. Very hard to do. Very hard indeed. What we've come up with is a few facilities that might help, that you might find useful, or we would certainly be using if we were benchmarking and stress testing one of your environments. So I'll begin by talking about the TPC benchmarks, the Transaction Processing Council benchmarks, and the HammerDB product. Now, TPC is an organized, well, we'll talk about what the benchmarks are, and HammerDB is a open source facility for simulating the benchmark activity. And we can use these tools to test the effect of upscaling activity on an existing database, predict the effect of changes. Maybe you can use it to compare performance of development and test and production environments, help you calculate hardware requirements. That's what we're going to be looking at. We'll also be using Oracle provided facilities, the Automatic Workload Repository, and the AWR Reports. These, of course, there may be licensing implications for using these, but interpreting these things, I won't say, it takes a bit of experience to make sense of these reports. There's a massive information into them, much of which is completely irrelevant to any one problem, but it's all there, and at some point you may find you need all of it. We'll look at a simulated case study where I'll go through using these tools in a demonstration of one approach for tuning a system to handle increased scale. We'll go through a simulated case study of doing that, and a brief word about alternative facilities. So that's our agenda. Now, the problem we're trying to solve, one technique for solving it, and maybe some other ways as well. So why do you need a workload simulator? Because many DBAs, including myself, have really no idea what will happen when workload increases. You size the system, you take a complete guess. Obviously, experience helps. You will have some feeling for whether a database instance is likely to need a 2 gigabyte SGA or 100 gigabyte SGA. You'll have some idea as to whether it's going to run well on one core or whether it might need 16 cores. You'll have some rough idea, but it's going to be very rough indeed. Now, as an example, a client of ours, we took them from an on-premises database to a cloud database that we host for them. The on-premises database, they're actually running on 8 cores. Well, 8 cores, Enterprise Edition, that's a huge investment. We looked at the workload, we looked at all the reports, and when we moved them to the cloud, we brought them down to half that number. That's a massive cost saving. And clearly, the original system was grossly overspecified. But how can you tell that? It's really difficult. And that's where a workload simulator can be invaluable. So you can see what will actually happen to your database, to your hardware, under a given workload. Such things will also help you compare performance across different environments. What would happen if you move from AIX to Linux? I don't know, but maybe a workload simulator will let you get some idea, predicts what the effects will be of going to a totally different environment. Configuration changes, database upgrades, what's going to happen then? And of course, application changes. What will the effects of those be? All very difficult to predict. And that's where a workload simulator could be, if you had one, could be so useful. And it's very difficult, in my experience, to do. Now, when you're talking about performance and scale, you can't avoid talking about benchmarking. And that's the key phrase, benchmarking. And when it comes to benchmarking, there's only one place to go, and that is here, not google.com. So that's the TPC. So the TPC has a bunch of members. TPC professional. No, it goes back a long time. It goes back, I think, to about 1985 historically. But the Transaction Processing Council has been developing over many years. They've been designing tests that will simulate, for the most part, interactive applications. They calculate the performance, and they go further than that. They compare them with the costs. And they publish a whole series of benchmarks on different types of application. The ones most people are going to be interested in are the transaction processing benchmark and the decision support benchmark, but there are several others, and there are variations of each one. So the sort of thing we get, well, the TPC-C is the OLTP workload, TPC-H, the DSS workload, but there are others. They publish properly audited results. For example, if we look at TPC, the top results, say by price, TPC, top results by performance. Let's go for, say, non-cluster. And here we have, as of 15 September, these were the, as of 15 September, these are the highest performing databases with fully audited benchmarks. And let's see, at the top we've got Alibaba Ocean Base, don't think anyone uses that. If I sort this by top performance results, let's see when we go down to database, that's not going to be a good one. Non-cluster only. I'm wanting to get to some that's a bit more realistic than some of these more obscure ones. Let's try all results. That's better. Right. So this was all the results for TPC benchmark. And we see the Alibaba, the Chinese one, comes in, and that's managed an extraordinary number of transactions per minute. But here, the number 3, Oracle Database 11G Release 2. That's pretty much out of date, you notice. Doing a TPC benchmark is a long process. It's expensive, it costs a lot of money, costs a lot of time, costs a lot of hardware, but it's all fully audited. There's all sorts of legal, it's wrapped around all sorts of legal restrictions as well. You can't fiddle it. You have to publish full disclosure documents. Exactly how was the database configured? What was the block size? What was the buffer cache? What underscore parameters have been set? What was the hardware? How is it configured? The full disclosure document gives complete details of everything. And what we see here is if we exclude the ocean-based ones, Oracle is up at the top with 30 million transactions per minute, and that was on a Spark supercluster, 2 through 4 servers. And that was back then on Solaris 10. Then we've got IBM with DB2 coming in next. Then Oracle on Solaris this time, still getting 8 million. Price has come down. That was only 55 cents per million, which is half the price, a lot less than nearly a third the price of the IBM equivalent. But this is attempting to give you an idea of what hardware, what database on what hardware gave what performance and what price you're paying as well for that performance. So these are the TPC benchmarks, and they're published with the full disclosure agreements, the full disclosure documents that explain how it was done. And these are fully audited. It should be really reliable information. Now, it's difficult to do though, very difficult to do. And for practical purposes, it's impossible for you to do on your own system, to run the tests on your own system in the official manner. You wouldn't be able to get the audited results. And that's where HammerDB comes in. HammerDB is a database load testing and benchmarking tool. You use HammerDB, well, it's open source and it's derived from the TPC benchmarks. You can't compare it to the real thing. And I would not think you could ever publish your results. You know, if you publish the results saying, you know, we use HammerDB to benchmark Oracle on Linux, Intel against DB2 on AIX, whatever, if you publish that, I wouldn't want to be, you might want to be a bit careful with getting sued by IBM or whatever as a result. You know, I don't think you can publish the results in any sort of public way. But for internal use, the HammerDB tests can be really, really valuable. So what does it do? Well, it throws a workload at the database. The database is configured with a test schema that's loaded up with data, and that test schema and the sample data are based on the TPC benchmark. You know, TPC defines exactly the tables that you're meant to be using, the structure of the tables, the data that's meant to be in it. And because everyone has those same tables, that's why the results should be comparable across platforms and across databases. So you can use HammerDB to build that schema, load it with data, and then simulate the workload of multiple virtual users against that database. And HammerDB, they've produced a few, but TPC-C, OLTP, and TPC-H, the DSS ones, are the ones that most people are going to want to use. So you can simulate transactional analytical scenarios, and the workload can then be used to derive meaningful information about your environments, such as how the hardware is performing before and after certain changes, perhaps how the database is performing before and after certain changes. And of course, you can vary the volume of workload you throw at the database to see how it will compare, how it will perform, perhaps as you scale up. If you look at, we just take it from their website. Oh, this is straight into the docs, and the documentation is a good starting point. Let me just take it from here. So, hammerdb.com, and this will take you through how to use it. And they publish versions of it for a number of databases. Yeah, there we go, SQL Server, IBM, DB2. It was originally written for Oracle, but they've since extended it to the other mainstream databases. Now, what does this actually do? Well, it doesn't do the real TPC benchmarks because they aren't allowed to. And that begs the question, what's the relationship between the HammerDB benchmark and TPC? That is explained in the docs. Here we have chapter 2 of the docs. What is TPC and T-proxy? T-proxy is the HammerDB version. Right. As they say here, yes, implementing a benchmark is a significant challenge. Right. TPC is the industry body most widely recognized, of course, and you can see the results. I just showed a couple on their website. Now, they have all sorts of rules for fair use, principal one of which is perhaps the full disclosure documents that have to be provided. T-proxy is HammerDB's variation. So it's open source, it's easy, cost-effective to run, open source variation, very similar, but you can't actually compare it. That wouldn't be fair. But within your own environment, you'll certainly be able to compare different configurations, different products, and get useful results out of it. Now, the workload we're going to look at will be the T-proxy, the OLTP one. And say T-proc-H, the DSS one, is also very interesting. But perhaps take a quick look at that, what a transaction workload is. And we're all DBAs here, but just to make sure that we are all on the same page of the workload. What is a transactional workload? Well, the database receiving requests for data, multiple changes, transactions, normal transactions. We have to have the ACID compliance, of course. And the standard TPC transaction is about half a dozen actions involving select, insert, update, and delete, and a commit. So the transaction isn't just one statement committed immediately. It's a bit more complex, a bit more like the real world. So that's the workload the tool we're going to use to simulate, to work out what's going on.
Yeah, can I just ask the attendees today, would you go ahead and use your question box to let me know whether you've got experience with HammerDB or another tool? And also another question, I'm curious to know whether you have worked with the TPC benchmarks before in any way, shape, or form. So HammerDB and TPC experience. Just curious about that. Thanks, John.
I would also like to add, if you ever had the experience of trying to write workload generators and you reckon you found a good way of doing it, do chuck that in as well. It'll be interesting to know. So you've thrown a workload at the system. You've got to make some sort of sense of it. That's where, assuming license permitting, we've got the Oracle's AWR, the Automatic Workload Repository. Now, its full use requires Enterprise Edition plus the Diagnostics Pack. If you're working on Standard Edition or Enterprise Edition without the Diagnostics Pack, then you've got Stats Pack instead. And Stats Pack, it gives you similar information, but it's certainly more awkward to use. So if you've got the license, you'll be using the AWR to analyze performance. So some configuration usually required, not much, but a bit. The configuration is usually to manage the snapshots. The Automatic Workload Repository is populated with what they call snapshots. Now, a snapshot is in effect a copy of a vast number of $V views. $V session, $V SQL, $V lock, $V wait event, hundreds and hundreds of $V views. And that's a snapshot is in effect a copy of them all. Actually, to copy the contents of hundreds and hundreds of $V views puts a dreadful strain on the database. But that isn't a problem with the AWR, because an AWR snapshot is generated by a background process, the Manageability Monitor background process. And that does not have to go through the SQL interface. It's written in C, you can use pointers, you can go directly to the C data structures that make up the instance and read the values. And that's why there's no real overhead to using the AWR. Your bypassing, it's not like StatsPack is different. StatsPack snapshots have to go through the SQL interface to actually look at the $V views. AWR snapshots do not. Some configuration of the snapshots is usually required, and that's simply to adjust the frequency. If, for example, let me get a window up. The my little database here. How is my AWR configured at the moment? Well, DBA hist WR control, workload repository control, and we see here that on my little database here, I have, just look at that view, just describe it. You've got the DBID, the snap interval. My snap interval, it's a interval data second, is there. I'm getting snapshots as an interval of every hour. And the other critical point is the retention. And the retention is this, 8 days. So what we have then is by default, out of the box, your database will take a snapshot every hour and keep those snapshots for 8 days. Most sites are going to change that. Most sites are going to change it. A typical change, you manage it with DBMS workload repository. This is the package that handles everything. And to adjust the snapshot configuration, you've got modify snapshot settings. And what you will usually change will be one or the other of the retention, the interval, possibly the top N SQL. That's the number of SQL statements that we captured into the workload repository. But these are the two that many sites will want to change, the retention and the interval. So remember, by default, you don't actually have much. Every hour, that may be okay, but you're only keeping data for 8 days. If something goes wrong, all of a sudden the database slows to a crawl, you're immediately going to say, well, today is Wednesday afternoon. What happened Wednesday last week? What happened Wednesday the week before that? And you'll want to compare the activity. Well, you can only go back 8 days. That isn't enough. So a typical change might be, say, this. Execute DBAs workload repository, modify snapshot settings. Retention, 8 times 144. The ints are minutes. That's going to put it to 8 days. I'm going to change that to 30 days. Let's keep 30 days worth of data. And the interval, instead of having the default of 1 hour, I'm going to make it every 30 minutes. That will be a typical change. So I've now upped my retention from 8 days to 30 days, and I've doubled the frequency from every hour to every 30 minutes. Note as a side effect, my AWR snapshots are now going to get 8 times as big. I've got to watch my sysawk table space because the AWR is going to get a lot bigger now. It's going to be a fair few gigabytes having made those changes. But that's a matter for you to decide on your site what sort of frequency you want. The general rule is the more often you gather the snapshots, the easier it will be to drill down to a small period of time. You might well find that with an hour, on average, everything was fine, but perhaps for a 10-minute period, things were pretty bad. More frequent snapshots would help you capture these spikes in activity, and clearly that's a good thing, so you can compare over a longer period. Well, you're gathering all this information. What are you going to do with it? There are a bunch of pre-configured reports, right? The reports show overall activity, and there are many variations of them that are provided, and various scripts you can generate that you can use to generate them. If you really want to, you can generate the reports with the API directly, and you can see the functions coming up here from the packages. DBAs workload repository, and then the various reporting functions. The diff report, for example, that will compare activity between 2 snapshots in 2 different instances, for example. And the very global one, that's going to be the rack-aware version of it. There are all sorts of pre-configured reports. Global always means it's rack-aware. The non-global ones are meant for non-rack environments. But generally speaking, you're not going to be running these functions. You're going to be running the scripts, the provided scripts that will prompt you for the time frame you're interested in, and will make appropriate function calls to generate the report. And I'll do that in a second. But what I'll do first of all is just to run through, have a quick look at one report from a live system. Of course, I can't use customers. We're strictly limited by customer confidentiality. This is a report I just happened to find on the internet. And as you can see, it's quite an old one. But never mind, it will do for the time being. At the header of the report, you get summary information, when the report was generated, a bit about the platform it was on. So this was running on AIX, 4 cores, exposed to Oracle's 8 CPUs, there's the memory and so on. The elapsed time, the report was between 1300 and 1500, so elapsed time 2 hours. DB time, nearly 4 times as much.
Pardon, John. For those of our students who are fairly new or new to the workload repository report, I really urge you to send in any questions you have now. Obviously, we can't spend the rest of our time on this report, but it's a really good opportunity to get answers from an expert on the AWR report. Thanks, John. Back to you.
We'll go through this pretty quickly, actually. I'm keeping an eye on the time. DB time then, what is DB time? In crude terms, it's the amount of time spent in the database server doing work for users or trying to do work for users. And of course, because Oracle is a multi-user operating system, a multi-user database, and we've got multiple CPUs, the DB time can be far greater than the elapsed time. because this machine can do lots of things at once. So that's the amount of time spent working or trying to work for users. So, and we can see here in DB time, we're getting about 2 seconds per second. Yeah, sorry, 2 seconds per second. So it's a bit over double. Is that good or bad? It's neither. The part of the report I normally start with is the time model statistics. This is the view, by the way, $, SQL time model. I forget what the view's actually called, but it's one view. It's a picture of one view. And what this is telling us is that during that 2-hour period, we had 16,000 seconds of DB time. And the arithmetic is perhaps up here. We saw the DB time as, we saw it as, oops, where it was, DB time, missing the figure, sorry, DB time 269 minutes. So if I take 269 times 60, so up there the units are in minutes, but now lower down the reports we find the units have changed to seconds. That's just one of these slightly annoying things, the way they jump around with units. So we have that much DB time working or trying to work for users. Of those 16,000 seconds, 15,000 were running SQL execution elapsed time, and another 190 seconds were running PL SQL. Depending on your environment, you may have a lot of PL SQL, and that's good news. If you add up that and that, you're pretty close to that. We aren't wasting time on parsing. We aren't wasting time on mucking about with sequences. No, we're working for users. We're running SQL and PL SQL. But here's the bad news. Of that 16,000 seconds, only 1,500 were actually working on CPU, less than 10%. So where has the DB time gone? About 10% of it was actually working. 90% of it wasn't working. This is a seriously bad situation. We've bought all this hardware, it's not doing anything. 90% of our DB time is being lost. If I threw another 50 CPUs at this box, wouldn't make any difference. The ones I've got aren't working. And you can see that down here, operating system stats. Idle time, 5 million seconds. Busy time, less than 500,000 seconds. The box is just sitting, wasting, it's just not doing anything. Why not? Okay. If it isn't working, it's waiting. And that takes us to the wait events and the wait statistics. And here we see the wait events sorted in order of how much time was lost. During the time of this report, we spent 7,000 settings hanging about on DB file sequential read. That was 44% of the DB time. We spent another 6,000 odd seconds hanging about on row locks. That was 39% of the DB time. These two wait events alone are what are crippling the system. So what do? You try to tune them. You try to remove these wait events. There will always be top wait events, but these are dominating the DB time. If we could somehow reduce these to 0, we would probably get a 10 times performance improvement by removing the 90% of the time that's spent waiting. It's never that simple though. I noticed in this report, look at this, the row lock contention. In fact, it occurred only once. There was one wait on row locks which lasted 6,000 seconds. That's probably an anomaly. It'll just be one problem. The session hanged on a row lock for nearly 2 hours. We can probably ignore that, but we certainly can't ignore this. These wait events occurred 3 million times and cost a lot of time. So you then have to drill down further and see what was the code that was hanging on that event. Right. And that would take you to another section of the report, which is the SQL stats. The DB file sequential read is a physical read from disk. So we get the SQL sorted on certain keys. Which SQL was doing all that disk I/O, all those reads? And here's the SQL ordered by reads. We've got a PL SQL call, that doesn't matter. What does matter is the SQL being called by the PL SQL. It's fairly obvious that that PL SQL call, which was 36.94% of total disk I/O, was actually calling this merge statement. So that merge statement is a candidate for some serious tuning. And you can click on here to get to the detail of it. And then you're into SQL tuning at that point. So that's a general approach to an AWR report. Look at the time model statistics and see, is the time skewed towards working or waiting? And in this case, it's definitely skewed towards waiting.
Sorry to interrupt, John. The SQL that you found, are you able to determine if that's SQL from an application or perhaps SQL from part of the system, if you will, sys?
You've got to talk to your users, talk to your developers. There's no good us as DBAs picking up a SQL statement and saying this one's hammering the system. It might be one that doesn't matter. You've got to talk to the application developers and see, does this SQL actually matter? Is it one of yours? This is a problem with trying to tune from an AWR report. You see a figure you don't like, a statement you don't like, and you try to fix it. Does anyone care? Possibly not. So that's the idea. Moving on from there, HammerDB. Right, so what we're going to do is generate a workload and then use HammerDB with HammerDB and then see what the reports are like that come out of it. To install it, it's dead straightforward. So I was showing, just in case you didn't get the website, you can download it from here, download, and it's a very small file to download it. I did the Windows version and install it, and there it is. It's just a client that's going to log onto the database. Having done that, having downloaded and installed, choose your benchmark, create the schema. So I installed it into Program Files, HammerDB, and there's a batch file, hammerdb.bat. So, and that will launch the tool. It's launched up on another monitor. There it is. So it's launched up, and there's a whole bunch, as you can see, SQL Server, DB2, MySQL, whatever. There are various supported databases, and for each database, we get the choice of benchmark. Just a moment, let me close that and do that again. DB.bat. Right. Yep, so you choose your database and choose if they want the TPC-C or TProc-C or the TProc-H. I'll stay with Oracle TProc-C. And then you have to build the schema. So I'll go through this quickly. Building the schema, a couple of options. It's all in the documentation in greater detail, of course. You tell it the TNS names alias you're going to connect to. I'll CLZ in my place. CLZ. It wants the system password, which is Oracle in my case. It's going to create a schema in a certain table space. So I better create that table space, TPC-C tab. TP table space, TPC-C tab. Number of warehouses. I'm going to go for 4. No, I'll go for 10. And the number of users to build it. This is all in the docs, but in principle, a warehouse supports a set of tables, a group of users, virtual users. The virtual users, every virtual user can simulate 10 connections. So I'm going to be simulating 40 sessions against 10 datasets. Then do the build. So it will now be creating it. And if we look at what's happening here, I ask for 4 virtual users, I get 5. There's one controlling session, and then all the others. And you can monitor what's going on while it's doing this. for example, if I were to see who's logged on at the moment, we can see that TPC, that was just counting up my users. TPC-C is logged on 5 times. That's these sessions here. They're creating the tables and trucking rows into them. It's a schema like any other. So what is in the schema? Well, if I do this, select object and object type from DBA objects, what is the TPC-C schema? It's call object name. Let's see, that's a bit better. A set of tables, index views. There's some more indexes that get created later on. So at this level, it's just a schema like any other. Remember, with the 4 virtual users, each one simulates 10 actual users working in one warehouse. And that is all detailed in the docs. This takes a couple of minutes for it to build. It's throwing in quite a few rows into these tables. When that is built, we can actually run the benchmark. Now, again, when running a benchmark, you decide how many virtual users. Remember, each virtual user is 10 simulated users. And by adjusting the number of virtual users, that's how you can scale up. And so you can scale up what would happen if I had 100 users, what if I had 200 users. But of course, you're working against the HammerDB schema. This is not your live application, but it's still going to give you a good general idea for how things will perform. In this database right now, and if I want to look at my wait events, I haven't got any wait events at the moment. That's good. It could be because it's nearly finished. Loading the stock tables at this point. But fairly soon that should be through. Then we can run the actual benchmark. While the benchmark is running, while the job that does it is running, you get AWR snapshots. It will take them automatically before and afterwards. And then it's an iterative procedure. You get the report out, make whatever changes appear to be necessary, and repeat. And you experiment with different workloads. Now, I'm going to dive into an example at this point. This is an AWR report that I got from running the HammerDB against an out-of-the-box database. I configured the database with DBCA, defaults all the way, no tuning at all. So this is my laptop, 4 cores, hyper-threaded. I ran it for just 4 minutes, which is too short for the real world. And in that time, I had 15 minutes of DB time. Looking at the time model stats, we see DB CPU was only 8% of DB time. So where's my DB time gone? Right. Foreground wait events, log file sync. That was taking 81% of my DB time. Log file switch complete switch. That was costing me another 8% of DB time. That was more time lost. So I'm losing all this time. This is where my time's going. These are the wait events that are causing my system to run so badly at this point, which is just out of the box configuration. So the question then becomes, what are these things and what do you do about them? Log file sync, any suggestions?
Yeah, John, I think I could give you a suggestion. So log file syncs, obviously it's got something to do with our log file. By the way, I like that the default configuration has sort of such a problem, but I guess can't be anticipated, everything. We're waiting on the log writer, if I've got this right, to write the log buffer to the log file.
That's exactly it.
And that's the wait event, log file sync. So
we've issued a commit, and our session is hanging until that buffer is written.
So do we have an application that's perhaps committing in a loop, too many commits, too aggressive on the commits? Maybe that would be a cause, perhaps.
Could well be.
Low
committing in a loop. Yeah, that sort of thing. Yeah, badly designed transactions could well be part of it. We're committing too frequently. Could well be it. If it isn't, there are some other things one can try to do. I'll show you what I did in a moment, because of course I can't tune the application because it's HammerDB. I would then be tuning the benchmark. So I can't take that approach. So in the real world, you definitely would. You'd see, why are we doing all these commits? Is there a way around it? I'm limited at this point to tuning the instance, not the application. I noticed that average wait 8 milliseconds. That's possibly quite long as well. Maybe the hardware has a problem. But anyway, that one, log switch problems. Okay, I didn't lose that much. I took two approaches to fix both of these. Firstly, I set these parameters. You'll have to look these up, of course, in the docs to be sure. I set commit wait to no wait and commit write to batch. This changes the algorithm used for commit processing quite dramatically. It removes the delay on commits. Whether you choose to do that, you'd have to look up these parameters and read up on them and see if they're appropriate for your environment, because they can, in some circumstances, be viewed as a bit dangerous. The other thing I did was reconfigure the redo log, because that's this one here. And what I did was increase the redo log files from 200 megabytes to a gigabyte, so that I'm simply not log switching so often. So that was the approach I took there. I couldn't adjust the application, so I adjusted the commit processing parameters and the redo log. And then what do you do?
Would a couple of questions in, would have increasing the size of the log files, larger redo, help here?
It helps here because we're not going to be log switching so frequently, and would also help with this one, but that's tiny. So making them bigger definitely helps, definitely. And that's what I did. I adjusted the commit logging, commit wait and commit write, and adjusted the redo log. And I ran the workload again. And what happened? Well, at this stage, if you go to the top, I was getting 377 transactions per second. Key commit metric, transactions per second. I made those changes, ran the benchmark again, and up pops this report. Elapsed time about 4 minutes or so, DB time about the same. But now we see that transactions over 1,000. Clearly those changes have worked. The redo generation rate, 7 megabytes per second, whereas previously 2.5 megabytes per second. So those simple changes appear to have increased throughput by a factor of nearly 3 times. But then we go down to I would go down to the side model stats. DB CPU is now 24% of DB time, whereas previously it was only 8.8% of DB time. So the machine's working much better. But we're still losing 75% of my DB time. Where's it going? Go to the wait events. Log file sync is still there, but it's not nearly as bad. The other log file ones have disappeared, but now this has popped up. Free buffer waits. DB file sequential read has come up. There's always going to be a top wait event. So we've increased our throughput by a factor of 3. That one we probably can't do any more about other than, as you were saying, Dave, tuning the application. But these, maybe we can do something about these. So, free buffer wait. What does that mean? Our session server processes want to copy data into memory.
Right.
They can't find a
I'm sorry. So let me take a crack. So the buffer pool is filled with dirty or pinned in use buffers, and we
correct.
Keep waiting to find a free buffer.
Because this is an OLTP application. We're doing loads of DML. We're copying data into memory and we're changing it. So if we want to copy more data into memory, we've got to write those change buffers back to disk. And clearly, how can we optimize that? There's one straightforward way. If we look at the DB writers, out of the box, I've got one database writer, because Oracle gives you one database writer per 8 CPUs. I often wonder why it's so low. Straightforward change, add more database writers. There's another one here, DB file sequential read. that is an I/O event as well, but that's not as significant as the others. What I did at this point was this, alter system set, alter system set. I raised DB writer processes to 4. That's going to fail because it's a static parameter, but we know what to do about that. Right. So what happened then? I reran the benchmark. Note at this stage we were getting, in terms of CPU of transactions, I was getting 1029 per second. So I just changed one more parameter, a bit more database instance tuning, ran the benchmark again. I'm now up to, I don't know if you were noticing the snapshot numbers. I'm now on snapshots 44, 45. Previously I was on snapshots 42, 43. So having raised my database writers, we find the transaction rate, ooh, I'm up by about another 30%. I'm up to 1300. So I'm now up to about, what, 4 times what I started with. And if we look at the CPU figures, it was at about 25%, wasn't it? We're now up to 32%. We are now only losing about 58% of our database time, or 68, I should say. And if we look at the wait events, right, 3 buffer waits is still there, but it's dropped right down. Log file sync is still there, but nowhere near what it was. And now DB file sequential read is the top wait event. Do you see the approach of iterative tuning like this? You keep making incremental changes, rerun the workload, see what to do next. What will we do about this one? We have to understand what it means, as with all of these things. And with all of these wait events, you look for them in the docs, you look for them in MetaLink, and see if you get anything helpful. But what we are picking out on ones are the ones that everybody knows, or every DBA will need to know. So DB file sequential read, what's that?
Right, John. I think that's the single block read. Well, a session waiting for a single block, as
That's
opposed
exactly
to
it.
a multi-block read, scattered read.
Yes, the multi-block read will be that one for the table scans. Single block reads. We're navigating indexes, probably. Also, since this is a DML environment, undo as well. Access to undo blocks is going to be block by block. So it's single block reads. We're getting the individual blocks. Now, there's not much you can do to tune that at the instance level. What you would do typically is find out which SQL statements are doing all this, these single block reads, and see if we can tune them. And that's where, having got to this stage in the tuning process, I would start looking at the SQL. And maybe if we look at the SQL stats, say elapsed time, which SQL statements have taken more time than anything else? Well, we've got a load of the new order PL SQL call. That was 30% of total time. That's the one that places a new transaction. And then we've got other ones. But the first bit of SQL that we've got is this update. Right. So what is that statement? Click on there. Update autoline, set that where. So we've got, and this is a statement you probably can't tune that much. It's almost certainly going to be updating a single line. What you would do at this stage, you found the SQL statements, whichever one you might want to be interested in. You find the SQL statements that are taking more time, or looking at the other keys, maybe doing more disk I/O, doing more CPU. You find the SQL statements that are causing problems, or causing problems for your users. You find them, and you attempt to tune them. To do that, you would begin by getting the execution plan out. AWR can do that for you. Take this one, for example. I could do with a slightly more complex one. Doesn't really matter which it is, but the AWR report can generate it. For example, I said I'll generate these reports with scripts. I'll go to RDBMS, DBMS, admin, AWR SQRPT, generate the SQL report. And the SQL report I'll have HTML report. And the snapshot range I was in was 44 to 45. So from snapshot 44 to snapshot 45. And choose the SQL ID that, in conjunction with my users and developers, we will have identified which SQL ID, which SQL statement needs to be addressed, which one is hammering the system, which ones are causing problems for end users and need perhaps to be improved. Take the SQL, I'm just picking one at random here. I don't suppose there'll be anything particularly interesting, but for illustrating the flow, it should work. Generate the report, give it a name, default name will do, and that just gets spooled out into your current directory, which will be, in my case, it will be my users directory. Users, me, there it is, generated. Wait, we're coming up to the end of our hour. And there we see overall information about the report and the SQL statement itself. Of course, this statement is incredibly simple. It's just an index range scan. But the principle, I hope, is there. You tune the instance to get rid of the wait events as far as you can. And when you can't get any further, look at the SQL and find out what tuning can be done there. Dave.
Thanks, John. So we're going to do two quick things. Just going to give you a 30-second background on Skillbuilders, services that are provided by John. And I'm going to send you a link to a whole bunch of tutorials. First, the services. So if your company, your organization, is looking to expand your DBA resources, adding a sort of a part-time DBA, if you will, consider us. Call us and we can assign John to help you out with some of the tasks, some of the projects that you guys are tackling. One of the things we've been doing a lot of lately is health checks. And these health checks are not only for security, but just the reliability, the recoverability of your database environment. And it's become a very popular service. And we can now include benchmarking and stress testing, either with HammerDB or another tool like JMeter, if you want to stress test using your workload. So these things are all part of our portfolio. Of course, tuning, database and SQL performance tuning is certainly in John's wheelhouse. There are 2 courses that are coming up that are listed on our website, the SQL tuning for developers and DBAs, and the performance tuning, database performance tuning, which I guess is a bit more specifically related to what we were discussing here today. So this database performance tuning workshop is going to start on September 20th and does have a lesson on the AWR, does have lessons on the wait events. So you'll get opportunity to learn about the wait events, see some case studies, and walk through some hypotheticals and some workshops hands-on. What would you do in this case to tune this situation? So those 2 classes are coming up. I'd like also, I'll put it in the chat right now. I'll put in the links to where to watch all of our free tutorials. And I'd like to also mention, I don't often mention this, but not only are these tutorials free, but they're ad-free. So as of right now, we don't allow ads in our tutorials, our videos on YouTube, which is where they're all hosted, right? But we don't allow ads in them. And I'd like you to note that difference between Skillbuilders and some other training providers, of which we are a part. So we're not injecting the ads and trying to make money from you that way. So all of these are free and ad-free, and there's dozens and dozens of DBA, Oracle database tutorials, developer tutorials in SQL and PL SQL, Apex tutorials, and more. So hope that does help you. And please, let's see, can you go to your last slide, John? And if imagine a JMeter.
Oh yes, this is the alternatives that we have.
Oh yeah.
Real application testing is Oracle's tool for workload generation. It's very good and it's expensive. I just checked out the pricing here. Real application testing, that's 11,500 per core. So it's an enterprise edition option. It's very good and can certainly stress test your environment. It records a workload. What we would use is JMeter.
Yeah, JMeter, we've had a lot of success with that in benchmarking Apex applications that we've written. And, so just answering, how many users, concurrent and, with some idle, some reasonably concurrent and flat out concurrent, how many users can we have on this database environment, on this running these Apex application? So it's a really nice thing to know that you've benchmarked prior to especially exposing your Apex application to the internet. You do some predictions on how many users you're going to have and make sure you can meet that demand. And if you use AWS for your hosting, like we often do, there's easy and dynamic ways to add resources, CPUs and otherwise, if the demand goes up. So AWS is another one of our strengths for not only Apex application hosting, but we do design AWS systems for customers as well. So please keep us in mind for that. John, got a question out here. Is there AWR SQL report for module name? If you see that question, John, from Kelly, maybe you need clarification on what's being asked for there?
Possibly, yes. I don't see the question. The SQL, no, you'd have to do that through tracing, I think. You'd have to trace through modules. To the best of my knowledge, AWR doesn't have a pre-configured report that lets you track activity by module, which is perhaps annoying. But tracing, you certainly could. I can't give an answer beyond that.
Okay. And we say tracing, John, SQL trace like we do in...
Yes, exactly. That you can enable per module.
Yeah, gotcha.
So this is the conclusion then. We need to simulate workloads. The way we would approach such things, HammerDB can give you an abstract workload, a simulated environment. There's going to test your hardware and your database instance. That's a good start. But then you need to test the application itself. And that's where we will go on with JMeter, do the stress test of your own software.